Okay, so basically, the files I'm going to use is those two files. Um, this does contains the code you probably will need to use for this assignment, and I copy down the code here into the MATLAB scripts for convenience. So be sure to look at those two files. Um, and also the function you download from core set, I tend to not change them. Um, for the reason I will mention later, and and one hint one thing I want to suggest is that the black box one objective function is very slow. So uh, if you want to test if your code is correct or not, do not use black box one objective function to test. You can try objective 3, 4, 5. They are much quicker. Okay. And one property of the MATLAB is that for file like this, it starts with function blah blah blah. The file itself is a function. Um, so you do so if you have a function here, you do not want to call the function inside the same script immediately. Uh, this is just that's simply not recommended for MATLAB doing that. What you want to do is if you want to call this function, you start a new script, just call this function, or you type the function in the command line. If you run this function, hold on, if you just so it's okay, so let's just so if you try to run this function, it will give you error. Because the file itself is a function, and by clicking run, it does not have inputs input parameters. So what you need to do is you can give an input parameter here, but I would not recommend to do that because that's not convenient to do. Simply because that. Okay, so we can start from the basics. We can start from the basic computations. If you want to assign a variable, like here, you just use this. You can see we have a that has value 1, and if you want to assign a vector, you can do that. If you use space between numbers, it will be a horizontal vector. If you use semicolons, it will be a vertical vector. And if you want to assign matrix to 3, 4, you can have something like that. And if you want to do matrix multiplication, you just use normal multiplier sign. And if you want to have a transpose, you just have this punctuation, and you got the transpose. Okay. Next is anomalous function. It's basically this. I'm having a function called f. Let's say it's just sin x. And if you have, you can, and it's you have if you put 0 here, it just gives you sin 0, which is 0. If you input a pi here, it gives you this is essentially also 0. So and if you have pi over 2, it shall give you 1. Yeah, and then it gives you 1. Next is about create a function. So basically it's just the structure like that. So you tell the MATLAB this is the function, and why is the variable you want to return. So if you have multiple variable you want to return, you just do something like that, and be sure to assign the value to x to the other variable you want to return somewhere inside the function, and something like that. And this is the function name. Make sure the function name is the same as the file name. Actually, MATLAB will warn you if the names are different, and this is the variable you want to input. Okay, let's go to symbolic computation. So you can create a variable like that. So if I just have variable x, you can say x equal to x, because x is just a variable. It does not have a numerical value. If you want to create a multiple variable, just do something like that. So now you see you have multiple variable here. But however, in the tutorial file, I'm creating variable like that. So why I'm doing that is that it's because in the objective function that you want to that you have in the assignment, for example, objective 3, the x is actually a vector. So of course you can create a variable vector like that by just put two univariants to a vector. But for convenience, you can also just create a multivariant here in this way. So what I'm doing here is you can see this x gives you corresponding to the x here. You can see if I'm typing xb here, I'll get xb1, xb2, and the array 2, 1 here means that I'm making this variable be a 2x1 vector. So if you want to create a variable matrix variable, say 2x2, you can see this is how you get. And then putting real here because the MATLAB default is making this variable be a complex number. So which gives you extra complexity here. So if you know your variable going to be a real number, just put a real to make things easier. Okay, so I'm having variable here, and I'm now going to create a function with variables. So I already make a function here, and I just put the x inside, and make it equal to f. So f here is going to be a function with variables. Although I'm using the function created by my own, but I'm creating those functions in a way that it has the same manner as the objective function provided to you. So so if you want to create um, so if you want to create a function with MATLAB, if you want to use the provided objective function to do symbolic computation, you just change the name to any function you want. Just change the object, something like that. Okay. Because they are created in the same structure. And if you want to compute a gradient, you just type gradient f, and you have gradient. You compute the Hessian, you have Hessian f. And then if you want to look at the determinant of the Hessian, let's make that easy. Just make the Hessian be h, and to carry the determinant. Okay, great. And I'm having the formula for the first order Taylor series expansion. And in the assignment, you all need to create the second order. Basically, what I do here is I'm using because the Taylor expansion is the first term of the Taylor expansion is the function value that's at the point that you want to expand with. So so I'm using x bar to represent that it's a fixed point, and I'm using x to represent this x can be any value. It's just a variable. It's not a given. So I'm just substituting x with x bar. So you see, So you see in the original f, those are x. But when you subs, it becomes xb. Yeah. And that's yeah, and that's all. You can just follow the same way to create a formula for the second order Taylor series expansion in your assignment. Okay, now let's okay, gradient hashing here. Okay, let's go to the plot here. So the plot is actually pretty straightforward. So we start. So by calling this, we will create a figure window, and I'm number this figure B1. So let's see. So you can see a window created here, and there's nothing here because I'm not plotting anything. And let's say I want to plot the sum function from -5 to 5, and the point one here is the step size. So this command will gives you an array from -5 to 5 with step size 0.1, so it increased by 0.1 here. And then you just do the plot. So you can see a plot here. And in the assignment, you're asking to do 1D and 2D cross-section plots. So basically, what does it mean is that, for example, if you have some function like that, you have a function with 6 variables. So which means that you will need to do a seven-dimensional plots, which is cannot be done with a single plot. So in this case, what we are doing here is that we say we have 6 variables. Let's say we are not interested in the change of the rest of 4 variables. We're just interested in the change of first 2 variables. So so we just we want to make first 2 variables change and make the rest 4 variables just be 0. Okay, so it's like if for the first 2 variables, I'm interested in the change from -1 to 1. So I'm creating here, and then I'm doing a mesh grid. So what a mesh grid here is that, for example, this is x-axis from -1 to 1. This is y-axis from -1 to 1. What mesh grid do is a mesh grid create the coordinates of all those points. But they do not save the coordinate of those points point by point. They save those coordinates into like 2 variables here. The capital X saves all the X coordinate of the points. The capital Y saves all the Y coordinate of the points. And then you just evaluate the function at each point, and you save this function evaluation to some matrix here, which is actually array. No. Let's see. Which is a matrix, and you can plot the function but using mesh or surf. So the difference between mesh and surf is that in the mesh you'll see a grid here, mini grid. But if you're using surf, you are it will color those grid. So I think in terms of in our case, mesh is easier to see, to observe instead of. So I prefer mesh here, but you can do anything you want. Okay. Oh, by the way, of course, if your function only have two variable, you do not need to fix any variable because because you can just do the plot. Okay. That's the part. Those code is also available in the slides. Okay, let's go to the optimization. Let's go to the solver. Um, in the assignment, you're asking to use 5 solvers. Those two, fmin search and the fmin USC uh already implemented inside the MATLAB. Um, and uh, those three functions, those three solvers are provided from Professor Taraki. So let's first look at fmin search. For how to use fmin search, just go it, and that'll be the first one on the page. So what we want to use, the statement we want to use is the last one. We want to have all 4 return variables. So inside the fmin search, you just put the function name, you put a starting point, and you also want to put the options here. So the option essentially is to control the display. So here means that I want to see how the function is optimized in each iteration. I want to make the maximum number of iteration be 10,000. For the tau fun and tau x, you can visit this link. So tau fun means that it's a tolerance for the change of the function value. So essentially, when your function changes very little in the solver, you may just want to stop because it's already reached the optimal. On the other hand, if your x changes very little, you probably also want to stop. That is probably because your x is also reaches the optimal. Okay. Okay. So this is how you import the function name. If your function is saved in other file, you need to put an @ before the function name. But if your function is anonymous function, say let's say f equals to @x, sin x, that can be sin x or example func x. If that is the case, you can just put f without h. It depends on you. Okay. Let's see. Okay. Let's put this in the option and we run the optimization. So what you have here is that you can see because I want to show all the iteration, we see all the progress of the iteration, and after iteration 25, the optimization terminate because it satisfies those two stopping criteria. And you can see the optimal value is 0, 0. Sorry, the optimizer of this function is 0, 0. The minimum function value is -1. The exit flag means that it shows how the function stops. So you see, here it shows the correspondence between the exit flag and what it actually means. As for the outputs here, outputs record the information about the number of iteration takes and the number of function evaluation. So those two will be needed in your assignment, and you can call this. You can get those number using dot, dot iteration, dot function count. This is how you get a number. Another function just work use different optimization method, but the code is basically the way you call this function is basically the similar. Just do the same thing. As for the function provided by Professor Talaki, like DFO, the DFO is constructing the same way as those two functions. So you don't need to worry too much about it. But the interesting is is those two solvers, those two solve for the maximum function value. So it has three output variables, three return variables. Those two functions has the same structure as you can see. So they are used in the same way, but they are different algorithms. So the x here is just the optimizer. F max is the maximum function value. NF is the number of function evaluations. So NF corresponding to this one, output of function count. So how do you get the function iteration, output iterations? You just it will actually print it out. So that's example. Start with say 1 1. One thing I forgot to do is that it look for the maximum. So it should to do is that because we know that the min on f is equals to the -1 times the it's equal to maximizing the negative value of the function, right? So we just create an anomalous function called let's say f flip. So x -1 times example. Okay. And then I'm calling f flip. Yeah. Okay. You can see it will print out the number of iterations. So you just record the largest number here. It will show you what's the optimizer, what's the optimal function value, the number of function evaluation. Just be careful with that because so we multiply -1 here. So when you record in your assignment, just make sure that you also times -1 to fmax. Okay. So how about the rest three input variables? So those two, I don't really think you need to worry about those two here. The thing you want to address is the stop it. The stop it contains those variable contains like 5 elements. I think really the first element is something you need to worry about because it controls the relative size of maximum simplex. So for example, the default is 10 to the -3. So if I want to say 10 to the -6, and I do not want to change the rest of 4 elements of the stop it, just you see in the first time before I import anything in the stop it, it had 1e -3 here, but I import -6, have 1e -6 here. Yeah, that's how this done. Uh, yeah, I think that's basically it.